Today we are going to talk about our central limit theorem. So as we're going through these problems today, and as we continue to go through a lot of the problems in the next couple of sections, next couple of chapters, the idea of our central limit theorem is going to become a big topic that we're going to revisit continually as we progress through the rest of the semester. So in the last section, we looked at some different simulations. And the big thing that we wanted to pay attention from those simulations was not necessarily the results of each simulation, but what happened when we increased our sample size. Right, so as our sampling size gets bigger, our shape of our distribution changed. Our shape of our distribution became more normal, and our standard error got smaller. So as we're going through our central limit problems, one of the things that we're going to be looking at and talking a lot about, especially in these first couple of examples, are the samplings that our data is coming from. So our central limit theorem tells us that if the following conditions are met, that the sample is random and independent, that we have a large enough sample, that we have a large enough population, then our sampling distribution is going to be NP, SE, P being our population proportion, SE being our standard error. Right, so as we're going through these different conditions, we have three big conditions that we see listed here. The first one is that our sampling is random and independent. This is going to eliminate bias, so this is going to give us accurate results. We have a large sample, and by large sample we mean that it is large enough to have at least 10 successes and 10 failures. So as we're going through these and thinking about these, that's what we're looking at for that large sample. And then a large population, our population must be at least 10 times larger than our sample size. So if all three of these first conditions hold, then our sampling distribution that we're looking at can be considered to be a normal distribution. And if we have a normal distribution, then we can go from there and we can answer some other types of questions. All right, so one of our simulations in our last section, we had a population of 1,000 and a sample size of 10. So when we were looking at this one, we took random samples. We got a visual image of our sampling distribution. But if we're looking at these and we're comparing these to our conditions for our central limit theorem above, it does not satisfy condition 2 of our central limit theorem. N is the size of our sample and P is the population proportion that we have. So our sample size is 10, our population proportion is 0.25, well 10 times 0.25 gives us 2.5. That's not large enough. This number that we get after we do our multiplication has to be greater than or equal to 10 to use our central limit theorem. So in this case, since it does not satisfy condition 2 of our central limit theorem, right, the sample size is too small, and we cannot use the central limit theorem. Central limit theorem being abbreviated with the CLT. Now if we look at one of our other simulations, our last simulation that we did, here we had a population of 1,000 and a sample size of 100. Now if we take this 100 times 0.25, right, we're going to get 25. So our sample size is large enough, our population is 10 times larger than our sample, so our third condition holds. Our first condition, that our sample is random and independent, we're going to assume that that is true unless we are told otherwise. But in this case, all of our conditions were satisfied. So since all of our conditions are satisfied, we can find our standard error for this problem. Our standard error formula that we looked at the end of section 7.2 says we take our population proportion times its complement divided by the sample size and then take the square root. So in this particular case, we're taking 0.25 times 1 minus 0.25 divided by our sample size of 100. So we have our square root of 0.25 times 0.75 divided by 100. As you're plugging these into the calculator, if you want to do it in steps, multiply, then divide, and then take the square root, or we can plug it into our calculator all at once. If we do that, we get 0.04 0.33, which if we look at our previous section and our notes, it's very close to the standard error that we see there. So what this means and how we're going to use this is if we are able to use our conditions of our central limit theorem and we are able to calculate a standard error, this standard error in combination with our population proportion that we have is going to give us our normal distribution. So the whole point of doing this is that we get our normal distribution, our n, and then our 0.25, comma, 0.043. I'm just going to round it off to that decimal place. Once we have this information, well, now we have a normal distribution like we used in section 6.2. Now we can answer questions about probability. What you see at the bottom of this page is exactly that kind of question that we're going to start answering. So when we're using our central limit theorem, step one is always going to be to check our conditions. So we're going to check our conditions of our central limit theorem, see if those conditions are met. Then we're going to find our normal distribution just as we did in the previous example. We're going to find our standard error and then figure out what that normal distribution is. Generally speaking, we're going to round our standard error to 3 decimal values if needed. And then we're going to go to our normal curve. And once we go to our normal curve, we're going to be able to estimate percentages just like we did back in chapter 6. Most of these problems as we're going through them and we're thinking about and using our normal curve, we're going to be using StatCrunch. So when we're thinking about our normal curve, we're thinking about going into, as we did in the last chapter, going into our stat menu, going into our calculator menu, and then selecting our normal curve. Right? Then we're going to enter in our mean, which is going to be our population proportion, our standard error, which we're going to use as our standard deviation, and then we can answer questions based on that. All right, so let's work through an example. As we're working through these, kind of a nice way to organize our thoughts, I have all of these examples set up and the ones in your mini quizzes set up where I asked you to fill out a few things before we actually find our percentage or probability that we're looking for. All right, so according to the Mars Company, packages of M&Ms contain 20% orange candies. Suppose we examine 100 random candies. Find the probability that our sample will contain 24% or more orange candies. All right, so we're going to start by listing what we know. Right, so N, our capital N, remember, is our population. So in this case, our capital N is going to be all M&M candies. Our lowercase n is our sample. So in this case, we have 100 random candies that were sampled. Our P is our claim, right? That's our population proportion. So our claim is that there are 20% orange candies. As we're working through these problems, we're always going to change our percent to a decimal. So we're going to have 0.20. So this P in our list here, this is our population proportion. All right, what do we want to know? Well, in this case, we want to know the probability that our sample is going to contain 24% or more orange candies. So what we want to know, I'm going to start with a capital P. That first P, right, as we saw in notation in the last chapter, stands for probability. So that P that's out front stands for probability, and it's capital P as compared to our lowercase p that is right here. Right? Then we're going to put our P hat in here next. Our P hat is our sample proportion. All right, so our P hat is our sample proportion. Again, all of these using the same letter, all of these different values meaning different things. All right, and we're asked to find the probability that our sample will contain 24% or more orange candies. So we're going to finish this off by saying 24% or more means we want a greater than, and then we're going to go 0.24 and finish off our set of parentheses. Right, so what we're looking for here is the probability that our sample is more than 24%. Right, now we're going to go through and we're going to check our conditions. Our sample is random and independent. We are going to always assume that this is the case unless we are told otherwise. Right, now we need to test our number of successes and failures. So we're going to test these two different statements that we have in parentheses here. So n times p is greater than 10. Well, n is our sample size. So our sample size is 100. Our p is 0.20. Right? And if we multiply 100 times 0.20, we get 20, which is greater than or equal to 10. So we do have more than 10 successes. Right, now we need to measure our number of failures. So again, we take our sample size, which is 100, 1 minus 0.20. Right? So if we work this out, 1 minus 20% gives us 80%. Right? So we have to have a 0.80 in here. 80% times 100 is going to give us 80, which is also greater than or equal to 10. So our second condition holds. Both of those inequality statements are true. One thing to mention here is that this NP that we have, this number of 20 that we came up with right here, this is our number of successes. Right? So in some cases, in some different problems, we might be looking for a specific number of successes, and we can always find this if it's not given to us by multiplying these two different values together. This n times 1 minus p, which gives us the 80, this is our number of failures. So in this particular example, we have 20 successes, 80 failures, which adds up to our sample size, which is 100, which should also hold as we're looking at these. So just to mention that if you're looking for your specific number of successes or number of failures, you can always find them by multiplying these different values that we have here. All right, now to finish our third condition, right, our large population, we want to make sure that our population size is larger than 10 times our sample size. Right, so our population is going to be all M&Ms, right, greater than or equal to 10 times 100, which is 1,000. We can assume that that is a pretty safe bet. Right, so there are more than 1,000 M&Ms in this world. All right, so our first step as we're doing our central limit problems is we are checking our conditions. All of our conditions hold, so we can go on to the next step. If any of these fail, right, then we cannot finish answering the question. So we do want to make sure we check all three of them. Again, the first one we're going to assume is true unless we're told otherwise that it's not, and we have to make sure we check all of these before we go on to step 2. All right, step 2 asked us to find our normal distribution. Right, so in order to find our normal distribution, we need to find our standard error. So same formula that are going to have started to see and will continue to see. We're going to take our 0.20 times 1 minus 0.20 divided by 100, because that's our sample size. Again, if you want to plug it into your calculator, multiply 20% times 80% divided by 100 and then take the square root, do it all at once. If you do it all at once, just be careful with your parentheses. And if we work this out, we get 0.04. Right, this value that we just got here, that's going to go up into our standard deviation part of our normal distribution. The number that comes up here is going to be our p from our original problem. So we're going to have 0.20, because that was our original population proportion, and 0.04, which is our standard error. Right, now that we have this information, we're going to go to StatCrunch. So we're going to go to StatCrunch, go into our normal calculator, right? And what we're going to do is we're going to enter, and I'm going to write it out for this first one. We're going to enter that our mean is 0.20. Our standard deviation is our standard error that we found, which is 0.04. Right? We have p, and then when we're looking in StatCrunch, it shows an x, but that x is our p hat that we're looking for. We're going to select our greater than or equal to, right? And we're going to type in 0.24. Because if we go back up to our statement of what we want to know, that's what we're going to plug into StatCrunch. So this statement that we had up here is what we're going to plug in, right? And this is going to be the answer that we are given via StatCrunch. Right? So if we plug this into StatCrunch, we get 0.159. Right. We're asked to sketch a picture and write our answer in a sentence. Right. So thinking about our picture here, our mean, our 0.20 goes here. And then if we use our standard deviation, we can go to the right and to the left by adding 0.4 each time. So we get 0.24, 0.28, 0.32 as we add, 0.16, 0.12, 0.08 as we subtract. Right? So we just found the probability, right, that our sample will contain 24% or more orange candies. Right? So 24% is right here. 24% or more was a greater than, so we're going to shade this area to the right. Right? So you can draw the sketch by hand, or you can use the one in StatCrunch that StatCrunch provides to assist you. And our final answer for this one is going to say the probability that our sample will have 24% or more orange candies is about 15.9%. All right, so working through this process, again, we started with a list of things that we knew, things that we were looking for. Again, we paid careful attention to our notation as we went through these. We checked our conditions to make sure that they were satisfied. Right, we found our standard error, and then once we have our standard error, we went to StatCrunch. Right, we entered these values up here, right, into StatCrunch, which then gave us, right, our probability that we were looking for, right, that 0.159, which is our 15.9%. Right, so we're going to work through some more examples. Right, so example 2, we're going to use our central limit theorem. This time we are going to be finding the approximate probability that the proportion of females in the sample will be more than 63%. So here we're looking at a statistic about vegetarians. So according to the statistic, 59% of all vegetarians are women. So our population N is going to be all vegetarians. Our lowercase n, our sample size, right, is we're going to say the 500 that were sampled. Right, our P is what's in our claim, right, 59%, which is going to give us 0.59. Right, what we want to know, again, our capital P stands for probability, and then our P hat is greater than or equal to 0.63. So what is the probability that our proportion of females in our sample will be more than 63%? Right, so we're going to go to our conditions. Right, our sample is random and independent. Yes, we're going to assume so unless we're told otherwise. At least 10 successes. Right, so we're using n times p. Our n is 500, our p is 0.59. So 500 times 0.59 gives us 295, which is definitely greater than or equal to 10. Then we're going to take 500 times 1 minus 0.59. Our complement of 59% would be 41%. 500 times 41% gives us 205, which is also greater than or equal to 10. So our second condition is satisfied. And then our large population, all vegetarians, greater than or equal to 10 times 500. Again, it's a pretty safe assumption that there are more than 5,000 vegetarians. As we're going through these, every once in a while you might have a problem with your population. Generally, if you're going to have a problem fulfilling your conditions, unless we're told that our sample is not random, which would affect our first condition, then a lot of times it's with our second condition. Okay. All right, now we're going to find our normal distribution. So in order to find our normal distribution, we're going to start with our standard error. So our P, going back up here, our P was 59%. So we're going to have 0.59 times 1 minus 0.59 divided by our sample size of 500. So we multiply, divide, take our square root, we get 0.022. So our normal distribution is 0.59, 0.022. Then we're going to go to StatCrunch. Again, we're going into our normal calculator. Right? We're using this as our mean, this is our standard deviation. Right? And then in this case, again, what we want to know, right, we're going to type in our probability that p hat is greater than or equal to 0.63. Right, so using StatCrunch, again, we can label the picture on our own or select the markings at the top to give us our different values for the bottom. So we have 0.59, 0.612, 0.634, 0.656, 0.568, 0.546, 0.524. All right, so we want to know our probability that we are greater than or equal to 63%. Well, that would be right around here. And we're going to shade our area to the right. Again, as within Chapter 6, if we have a small area shaded, it should be a small percentage, large area shaded, a large percentage. So in this case, we do have a small percentage. So the probability that our sample will have 63% or more females is about 3.5%. Again, that 3.5% was generated using StatCrunch. So we're going to continue to go through a few more examples here. We're going to kind of go through the same process every time. Based on the type of problem, we might be asked for a slightly different kind of setup for our question. So as we're going through the next couple of examples, we're going to talk about and answer, instead of just being asked for a probability, maybe asked to make a decision and or bring something else that we've learned about statistics into our process as we're going through these problems. Right. So in a closely contested school bond election, polling indicates that 50% of voters are in favor of the bond and 50% are against the bond. Suppose a random sample of 80 voters is selected. Use the following to approximate the probability that the sample proportion will fall within 2 standard errors of our population value, which is 0.50. Right, so our population, right, is all voters. Our sample, right, the random sample of 80 voters, so 80 randomly selected voters. Right. Our proportion that we're testing, right, is 50%, which is 0.50. Right, so as we're going through this one, this is going to kind of walk us through and ask us a few different questions. So we're going to slightly vary our steps that we saw in the last couple of examples. There's a couple of homework questions that are set up this way. So what percentage of the sample would we expect to favor the bond? Right, well, we would expect 50%. Right? So right now polling indicates that 50% are in favor, 50% are against, so we should expect 50%. Then we're asked, does our central limit theorem apply? This would be our first step, checking our conditions. In this case, and you're going to run into this in a few homework problems, other things, we're going to skip them, assume that they are all met. They are all met. We're just not going to work through every individual condition for every single problem that we're going to go through. All right, then we're going to find our normal distribution. So we're going to find our standard error. So we're going to take 0.50 times 1 minus 0.50 divided by 80 and take that square root. We get 0.056. Okay. So 0.50 is our first value. That's from our p up top here. And then we're going to do 0.056 for our standard error that we just found. Okay. All right, if we can use the central limit theorem, which we can, what is the approximate probability that the sample proportion will fall within 2 standard errors of the population value, which is 50%? So first thing we're going to do is we're going to find those values. So 2 standard deviations, or 2 standard errors, below the mean would be 0.50 minus 2 times 0.056. Right, we could do 0.50 minus 0.56 and then subtract again, or we can plug it into a calculator this way. We get 0.388. Right, now we're going to do the same, but we're going to add. So we're going to take 0.50 plus 2 times 0.056, and we get 0.612. What that means in this case, what we want to know, this is a case where we're looking at a between probability. So we want to know the probability, right, that our p hat is between 0.388 and 0.612. So that means when we go into the StatCrunch, we're still going to select our normal calculator, but we're going to choose a between case this time. Right, so labeling on the bottom, we have 0.50, 0.556, 0.612, 0.668. Moving to the left, 0.444, 0.388, 0.332. And we are looking for between this 0.388 and this 0.612. All right, so we're going to shade this area here in the center. Again, then as we go into StatCrunch here, we're going to go into our normal calculator. Once we're in our normal calculator, we're going to choose the between, right? And we're going to put our 0.388 for the left one and our 0.612 for the right value. And then after we select compute, we're going to get 0.9544. So we're going to say the probability that the sample will fall within 2 standard errors is about 95.4%. Right, now, if we think back to what we talked about in previous sections and throughout the semesters, we talked about our empirical rule, right? So just kind of a reminder, right? Our empirical rule tells us that we have 95%, right, within 2 standard deviations. So what we got as an answer here should not be a big surprise at all. We actually get something that's just a little bit more exact than what we get with our empirical rule. All right, so our next example, we are going to use this to answer a question. Right, so a survey of eating habits showed that approximately 4% of people in Portland, Oregon are vegans. A restaurant in Portland expects 300 people on an opening night, and the chef is deciding on the menu. Treat the patrons like a simple random sample of the 600,000 people surrounding Portland. If only 14 vegan meals are available, what is the approximate probability that there will not be enough vegan meals? Okay. So our population is the 600,000 people that surround Portland. Okay. Our N, our sample, is the 300 random patrons that decide to visit this restaurant on opening night. Our P, right, is 4%, which is 0.04. Now what we want to know the probability that there will not be enough vegan meals. So we're looking for the probability that P hat is greater than or equal to 15 over 300. Okay. The 15 comes from how many he's preparing. Right? If the chef prepares 14, well, 14 is enough. But if we have more than 15 people that come in that are vegans, that's not going to be enough. Right? So in this case, we're looking at this actually as a fraction or a ratio. We're going to change this to a percent and change it to a decimal. So we're going to say the probability that P hat is greater than or equal to 0.05. If you divide 15 divided by 300, we get 5%, which is 0.05. Step 1, our conditions. Again, we're going to skip it in this case. We're going to assume that they are met. Step 2, we are going to find our standard error. Right. So our P is our 4%. So 0.04 times 1 minus 0.04 divided by our sample size, which is 300. This gives us 0.011. So 0.04 is our first number here. This is 0.011 that we just found for our standard error. Right, that's the second number. So when we're entering values into a StatCrunch, we're going to enter that one for our mean, that one for our standard deviation. Okay. All right, so now we're going to find our probability using StatCrunch. Right, so I'm going to label my horizontal axis here, 0.04. Again, moving up and down each time with my standard error. So 0.051, 0.062, 0.073, 0.029, 0.018, 0.007. All right, and we are asked for the probability that there will not be enough vegan meals, which was 5%. So 5% is right around here, and we're going to shade this area to the right. Then using our normal calculator in StatCrunch, we get 18.2%. So we're going to say the probability that the chef will not have enough vegan meals is about 18.2%. All right, one last example to wrap this up. We're going to go through, start with the same process. Again, answer a slightly different question here and talk about a couple of different possible other ways of figuring out the same answer. All right, so in example 5, right, according to the American Veterinary Medical Association, 36.5% of all Americans own a dog. Suppose a random sample of 200 Americans is taken. Would it be surprising, remember surprising meaning more than 2 standard deviations from the mean, right, to find that 45% of the sample owned a dog? Right, so our population is all Americans. Our sample size is 200 randomly selected Americans. Our P, 36.5%, or 0.365. And what do we want to know? Well, we are asked, is the probability that our sample is more than 45% surprising? All right, so what this means is more than 2 standard deviations away from the mean. Going back to our empirical rule, I'm going to draw out a little sketch here. So when we're thinking about our normal curve and our empirical rule, we have our mean in the middle, and then we go out 3 standard deviations in each direction. So this is our mean. There's +1, there's +2. There's -1, there's -2, and in the center part here, we have 95%. So if we label these mu plus 1 standard deviation, mu plus 2 sigma, 2 standard deviations, mu plus 3 sigma, mu minus 1 sigma, mu minus 2 sigma, mu minus 3 sigma. We have 95% using our empirical rule that's between 2 standard deviations. So what that means is in both of these tail ends here, if we subtract 95% from 100%, we have 5%. We take half of 5%, well, we get 2.5%. So one way we can look at this question is not just say, is this surprising? We could say, is the probability that p hat is greater than or equal to 0.45 less than 2.5%. So that's what we're going to be looking for. All right, our first step, checking our conditions. Again, we're going to skip it. So we're going to jump right to our standard error. So we're using our 36.5%, so 0.365 times 1 minus 0.365 divided by 200 is going to give us 0.034. So we have 0.365, 0.034. Apologize for the timer. And then we're going to go to StatCrunch and we're going to use our normal calculator. So our 0.365 gets labeled in the center here. We're going to go up and down by our standard error each time. 0.399, 0.433, 0.467, 0.331, 0.297, 0.263. So looking at this, 45% would be somewhere around here. And if we type this into StatCrunch, we're going to get the probability that our sample will have 45% dog owners is about 0.6%. So using our normal calculator in StatCrunch, we get 0.6%, which is this tiny little area down here. Both looking at our picture and both looking at our percentage, right, this should be surprising. So we're going to say, since the probability is less than 2.5%, yes, it would be surprising. Right, Right? So one way to answer this question, we go through, we use our central limit theorem, we figure out our probability that we're going to be more than 45%. Right? It's a very small percentage, less than 2.5%, so it would be surprising. We do have a couple of other different ways of thinking about this or working through this. So I'm going to go back to kind of my summary here and use that with the questions on the next page. So one alternate method, we could use our empirical rule. Right. So we need to find percentages that are 2 standard errors above the mean. So our mean, or our population proportion, was this 0.365. And then we're going to take 2 times our standard error that we found here, times 0.034, which gives us 0.433. And then we could say, since 45% is more than 43.3%, which is 2 standard errors above the mean, yes, it would be surprising. So in this case, we actually don't need to use StatCrunch. Once we found our standard error, we can use our standard error then to go along with our empirical rule. Okay. Our second alternate method, right, is we could find our z-score. So our second alternate method would be finding and using our z-score. Right, again, we would still need to find our standard error that we did on our previous page. But we could do z equals 45%, so 0.45, minus our mean, which is our population proportion of 36.5%, so 0.365, and then divide it by our standard error, 0.034. This gives us 2.5. So our z-score is 2.5. Going back to chapter 3, again, anytime we have a z-score that is more than 2, right, it is surprising. So we could say, since the z-score is greater than 2, yes, it would be surprising. All right, so as you're going through the homework problems in this section, some of them are just asking you to find probabilities. In that case, you're going to use StatCrunch and your normal curve to find those probabilities. There are going to be some other questions that you're going to run into in your homework that are tied into other material, such as our empirical rule and z-score.